Good morning, colleagues. Good morning, colleagues.
Good morning, Prof.
Thank you. You're welcome.
Professor Odo.
Okay, I can hear you,
Professor.
Yes, thank you.
Okay, thank you.
Professor. Yeah. I welcome you all to this seminar. Today is one of our regular seminars, and this is our seminar for the month of February, which is holding today, the 11th day of February 2025. And today we are going to listen to one of us, a renowned researcher, Dr. Alicreance Hiyadutuje. Sorry if I didn't get the name correctly. Dr. Alicreance is a physicist. He has his PhD in physics, specializing in ionospheric studies at the University of KwaZulu-Natal in South Africa. And currently, Dr. Alicreance has a broad experience teaching physics, ionospheric physics, across different institutions in South Africa. So today he's going to talk to us on a topic, ionospheric waves. And I think that will be very interesting. We'll be happy to listen to him. So, yeah, Dr. Alicreance, over to you.
Okay, thank you. As you have introduced me, my name is Alicreance Hiyadutuje. I'm a postdoc researcher at the SANSA. And today I'm going to talk about the ionospheric waves. So I'm going to introduce the space weather. Then after, I'm going to define what is a wave. Afterward, I'm going to give you different types of waves that are in atmosphere. And after, I'm going to tell you about the application of the traveling ionospheric disturbances. Then at the end, I'm going to give you some brief introduction of the advanced theory of the gravity waves. So then I'm going to summarize and give you a short test, but that quiz is for only students who are participating in this seminar if they are there. So the space weather is similar to our terrestrial weather, but this weather happens between the sun and the earth, where you have the coronal mass ejection. Coronal mass ejection are a huge mass of plasma that are ejected from the sun, and they can travel all the way from the sun to our atmosphere. So the second parameter we are going to see is the solar wind. This is those are particles that are also traveled from the sun to the earth, and they can travel at the speed of more than 1,000 kilometers per second. So the third phenomena is called the solar flare. Solar flares are explosions that are caused by the travel of the charged particles that travels at the speed of light. And they can take only around 8 minutes to travel from the sun to the earth. So all of those phenomena, they happen at the surface of the sun, where it is called the sunspot. So when you have a many number of sunspots, that means you're going to have more activities, which means the space weather is going to be bad if you are trying to compare the space weather as the terrestrial weather. So that is when on the Earth, we say that we have a bad weather or cloud, rainy, whatever. So that is in a similar way. So there's phenomena from the sun, then they impact our atmosphere, which is a part of which contain our ionosphere. So the region of atmosphere, you have the atmosphere has 5 main layers. The first one is troposphere, which ranges from 0 to 12 kilometer. You have a stratosphere between 12 to 50 kilometer. You have also mesosphere from 50 to 85 kilometers, and the thermosphere from 85 to 600 kilometer. Then the last layer is called the exosphere, which is above 600. So on this graph, you can see the way the regions are, the layers are arranged. Then what we call ionosphere is the region between 50 to around 1,000 kilometer in altitude. So this region, it covers mesosphere, thermosphere, and a part of exosphere. And this region has 3 main regions. Here on the right-hand side, you can see the figure. So it has what we call D region, it has E region, and F region. So these regions are numbered based on the alphabet. So the first one which was discovered was the electric field, the E region, because of the electric field which was found in that region. Then later they find that there is another region below it, they called it D, and then the other region which was discovered above it or on the top of the E region was called the F region. So F region has 2 regions. During the day, it has F1 and F2, while during the night, you have only F2 because the activities of the sun. So this region, the ionosphere, it depends on the sun. When the sun is present, that means you are going to have a larger region. But when the sun is set, after the sunset, the region reduces its size, then you have only F2 region. Other regions, they disappear. E and D region, they disappear during the night. So now in the ionosphere, we have many phenomena. We can see that when you have the solar flare from the sun, it may ionize the particles and of course, increase the size of the ionosphere. So let me start from left side. You can study what we call the traveling ionospheric disturbances in the ionosphere. You can also find what we call sporadic E layer or meteor echo. You can also find the gravity waves that can propagate upward in the ionosphere. You have also what we call field-aligned current. You can also have MHD waves. These are magnetohydrodynamics waves. You can also study the ionospheric irregularities, including aurora, tongue of ionization, plasma convection, and other many stuff in the ionosphere. So all of those phenomena, they affect different technology, especially when you are using your satellite or when you are using your HF communication, you may be impacted by these waves. So today, I'm going to focus on the traveling ionospheric disturbances, or which are usually caused by gravity waves. So we are going to start by defining a wave. What is a wave? So a wave is a flow of transfer of energy in forms of oscillation through a medium, or simply you can say is the transfer of energy from one place to another, but in forms of perturbations. So, for example, you have a sea wave, tide, sound, light, and even the movement of small plants which are blown by the wind. Those are the examples of waves. So those waves are used in many fields of physics, for example, for communication. And they have three different types of those waves. You have a mechanical, we have a electromagnetic, and we have a matter waves. So mechanical is divided into two, longitudinal and transverse. So longitudinal, if you can see on the right-hand side on this figure, are the waves that are when the particle displaces along the propagation of the energy in the same direction. That means the wave energy and the particle, they move all in the same direction. Then you have what you call longitudinal waves. But when the particle moves in a perpendicular direction to the energy flow, then you have what we call transverse wave. So in our case, today we are going to focus on the transverse waves, which are called the traveling ionospheric disturbances. So those are the definition. And here, what I can mention also is that waves, especially the transverse wave, they have a crest and they have a trough. So if you move from one trough to another one, you have what you call wavelength, and you can also have the amplitude. As we are going to see in the next slide, amplitude is this distance from the rest position to the maximum displacement of the wave. So characteristics of waves, we have the amplitude. So waves have amplitude, which is the maximum displacement or distance moved by a point on a vibrating body or wave measured from its equilibrium position. So as I have shown, is this distance from here is called the amplitude. And usually its unity is in a length unity, which can be meter, kilometer, or other units of distance. Then we have a period is the time taken for two successive crests or pass a specified point. So for example, if you record the time here and the time here, the difference between the two time is going to be your period. So it can also be defined as the time taken from the wave moving from this point and come back to the same position. So that time is the period of the wave. The wavelength, as I have already defined it, is the distance of consecutive trough or consecutive crest. So when you measure the distance between those two, you have your wavelength. And the frequency is the inverse of the period. So here I have a different formula. This is, you take time divide number of cycles, or simply you take the frequency and you take 1 divided by the frequency if you have the frequency. Then the last one is the speed or phase velocity. Sorry? Okay, I think there is no problem. So the last one is the phase velocity, which is actually you take wavelength divided by the period, then you get what we call the phase velocity. So this is the simplest formula you can use to calculate the parameters of the wave. And now we are going to see what are the atmospheric and ionospheric waves. So we have different types of waves in the atmosphere as well as in the ionosphere. So the first one are called the planetary waves. Planetary waves have a period between 2 to 16 days, which means you have a crest today and you wait 16 days to have the second crest. So their wavelengths are between 3,500 up to 10,000 kilometers. They are caused by temperature difference between polar air and tropical air, as the Coriolis effect varies with latitude between the troposphere and mesosphere. So generally, those ones are called by terrestrial weather. So how the weather behaves and the temperature, pressure, everything. So when there is they say corrotating effect, then that's where you have those planetary waves, which are very long in terms of period. So you have to wait for half a month to get the peak or the next crest. The next type of waves are called tides. Tides, they have a period between 8 hours and 24 hours, which is 1 day. So which means you have to wait. If you get a peak today, you have to wait up to tomorrow, the same time, to get the next peak of those kind of waves. So their existence is influenced by the sun and the moon. They are influenced by gravity and may be produced by heat as a result of absorption of solar radiation by water vapor and ozone in the mesosphere. So they have three types. You have a semi-diurnal, diurnal, and the terdiurnal, depending on their periods. Their wavelengths are between 40,000 and 20 kilometers. So they have a very long wavelength. Now the third type are called sound waves. So sound wave is a vibration that propagates through the medium in the form of mechanical wave. So we have found that this is, sound wave must be longitudinal wave. They are also found in the atmosphere. And the pattern of disturbance caused by the energy traveling away from the source of the sound. So sound waves are longitudinal, as I have said, and for example, as we are going to see in the next slides, we are going to see that the volcano, they can produce actually sound wave when they are erupting. The fourth type of waves are called the atmospheric gravity waves. So those are the kind of waves we are going to focus on during this presentation. The atmospheric gravity waves are caused by buoyancy force, which acts, of course, upward against the gravitational force. Always, anything that has a mass in atmosphere, it has the gravitational force, because gravity is acting, pulling that object downward. So then when there is any perturbation or disturbance on the atmosphere, gravity tries to restore the equilibrium of that object and end up by producing waves. So those waves are now referred to as the atmospheric gravity waves. Other waves that are not very important today are called ionoacoustic waves in ions, electroplasma waves in electrons, and others are called the MHD waves. These are waves that you find in plasma. So now we are going to focus on the gravity waves, atmospheric gravity waves. As I have mentioned, you must have the upthrust, which is defined by this term, and your gravity. So this is the mg height, this is density, and the gravity. So when they are in balance on this figure, on the top figure, I'm trying to show that this is a cloud which is in balance, where we can assume that the upthrust is equal to the gravity or gravitational force. So the force which is acting upward is equal to the force that is acting downward. So that means the cloud is going to be in equilibrium. But from the definition of gravity waves, if you have any perturbation on this cloud, you are going to have the waves. Those waves are called the gravity waves. And you can see the figure at the bottom, that you can see the structure of the cloud is completely different from the one on the top. So those, you can even see them during the day by your eyes, your naked eyes. outside most of the time when you see those kind of crowds with those regular patterns. Those are gravity waves that are propagating in the crowd. So gravity waves are divided into 3 groups. You have a large-scale gravity waves, atmospheric gravity waves, with wavelength of more than around 1,000 kilometer, period of 30 to 180 minutes, which is a half an hour to 3 hours, and the phase velocity is between 500 and 1,000 meter per second. The second group is the medium-scale atmospheric gravity waves with several hundred kilometers of wavelength. Their periods are between 5 and 60 minutes, and the phase velocities are around 100 to 300 meters per second. The last group is called the small-scale atmospheric gravity waves with very short wavelength and very short period, 2 to 5 minutes. Their phase velocities are between 300 to 3,000 meters per second, so they move very, very fast. Of course, atmospheric gravity waves causes, or they can cause what we call the traveling ionospheric disturbances. Now, so there are 4 waves or 4 methods by which those waves can propagate. The first one, as you can see on this graph, they try to show this is the height from the ground to the thermosphere. Now you have a source of the wave. Let's suppose that the waves are generated at this position. So they are going to have different, of course, different way of propagation. The first one is going to move like this one, as you can see in the mode number 1, which means they can propagate far away from the source. So these ones, number 2, they propagate close to the source. Number 3, they move downward to the ground. They can also reflect upward and they move far away from the source. While the number 4, they remains close to the source, to the generating source. So those are 4 types of propagation of the gravity waves, which are generated in the thermosphere, which is your ionosphere in the E region. So now, TIDs, or traveling ionospheric disturbances, they were discovered in 1948 by Mono, and they were reported to be caused by gravity waves, atmospheric gravity waves. They also have the same, almost the same characteristics as those of atmospheric gravity waves. They also have 3 groups: large scale, medium scale, and the small scale traveling ionospheric disturbances. Sorry. How do you estimate the characteristics of medium scale traveling ionospheric disturbances? So when you have a time series, your data recorded by any given instrument, you can compute the parameters of those waves. As we have seen, your waves must have a amplitude, period, the frequency, wavelength, and the phase velocities. So first of all, you must use, there are many methods, but here I have choose fast Fourier transform. So the fast Fourier transform can give you the period. Then once you get the period, you can estimate the wave number along X direction and along Y direction. That means you are assuming that those waves, they are moving in a plane. So along X and along Y, then you can calculate the resultant wave number by using this formula. Then you can calculate your wavelength by using this formula, 2 pi divided by that wave number. After you get the wavelength, you can divide your wavelength by the period obtained using FFT, and then you get phase velocity. Then lastly, you can find the direction, which is your propagation or propagating direction. So in which direction are those waves propagating to? So you have to use the inverse or arctan of kx divided by ky, then you get the propagation direction, which is starting from your x direction. Your reference point will be your x direction. So those are the examples of the result which we published last year. In this paper, we're studying the statistics of TIDs and other mechanisms, which we call the near-range echo using Superdan ladder, which is located at Zongshan in Antarctica. So we found that, for example, for these 5 events, which we can call TIDs during 5 days. So the first one, the second, the third, the fourth, and the fifth, we estimated the period using the FFT, and then we calculated the wave number long X, wave number long Y, and then we find the resultant, which is given by the formula on the previous slide. We estimated the azimuth. We estimated also the wavelength. As you can see that their wavelengths are around the 500, 600, 400 kilometer. We estimated the phase velocities in meter per second, and this is another parameter which is amplitude. Of course, this is amplitude in kilometers we estimated from those kind of waves. So this is the simple way we use to estimate those waves, but it doesn't mean that it is always very simple to estimate the waves. So as you are going to see at the end of this presentation, sometimes if you want to do modeling or simulation, you need to go deep into other complicated theories. So what causes TID? First of all, I have said TIDs are caused by atmospheric gravity waves. So simply, gravity waves are generated in the troposphere or stratosphere of our atmosphere. And then when they propagate upward, they may dissipate. And while dissipating, they are converted into the TIDs. So energy is not lost, it is converted to the TIDs. So this is the formula which is actually showing the perturbation of electron density. That is actually the definition of TIDs, because TIDs is only measured in the ions and electrons, while atmospheric gravity waves are found in neutral particles. So the figure on your right is showing you that most of large-scale traveling ionospheric disturbances are generated at the pole or in the polar region, especially during geomagnetic storms. So your figure to the left is the waves in water or ocean waves, which actually is in an illustration of how those waves will look like in the ionosphere if you can replace the water by electrons or ions. So you will have this kind of perturbation in the ionosphere, which are similar to the ocean waves. Now, traveling ionospheric disturbances are also caused by volcanic eruption. So simply here you have this diagram to the right. It shows a volcan that is erupting. This volcan, once it erupts, it creates acoustic waves. And as we have seen that acoustic waves, they propagate along the propagation of wave energy. So those atmospheric waves, those acoustic waves, they move upward and they reach the ionosphere in the E region, where they create E region dynamo and cause the total electron content to be perturbed, or they cause the electron density to be perturbed and they create traveling ionospheric disturbances. So this, if you want to read more about the volcanic eruption and how they can generate the TIDs, you can read this paper by Shinbori. So, of course, they were also reporting that these waves that are generated in the southern hemisphere can propagate or can be found in the opposite hemisphere, which is northern hemisphere, by using this circuit, which is the electrical circuit. If you understand the electricity, you can understand this diagram by checking the electric field, because those of course those traveling ionospheric disturbances, they also generate their own electric field through polarization. So that is volcanic eruption, which can also cause the TIDs. The next is what they call super typhoon. So this is a mature tropical cyclone that develops between 180 and 100 degrees in east in the northern hemisphere, which is also known as hurricane. In tropical cyclone in the northeast Pacific or North Atlantic. So those also, they create TIDs, and they were reported by this person, Chu Min Yang. So if you are interested, you can read the whole story here. So as you can see, they found that after you have that cyclone or hurricane from this location or here, they observed the TEC perturbation in ionosphere, which has similar perturbation as the hurricane. So they concluded that those TIDs were generated by hurricane. The next method where TIDs are generated is called the thunderstorms. So thunderstorms also were reported to cause traveling ionospheric disturbances. For example, if you have a thunderstorm at this location, Liu Tong and other researchers found that after the thunderstorm which were recorded at this location, they found that the total electron content in PRN number 2, PRN number 6, and PRN number 5, they were showing the perturbation of electron density after a few minutes, which means that this thunderstorm was the generation mechanism, or was associated with those perturbation of electron density, hence the cause of those traveling ionospheric disturbances. The other methods where TIDs are generated are called the substorms. Substorms is a brief disturbances in the Earth's magnetosphere that cause energy to be released from the tail of magnetosphere and injected into the higher latitude ionosphere. So those are the phenomena which are associated with space weather. Of course, far away in the magnetosphere, when the magnetosphere are perturbed, of course, they found, you can read more about these substorms and how they generate traveling atmospheric disturbances by of course, we have the they use magnetometers where you can observe the magnetic field. Magnetic field, when they reach a certain level of disturbances or perturbation, then they can say that this perturbation was caused by a substorm, and then that substorm was linked to the traveling atmospheric disturbances in this figure below. So we have many phenomena or many physics which can cause by which the traveling ionospheric disturbances are generated. The other one is called the Lorentz force. This is the reference. You can read more about this mechanism and how they can generate TIDs. Atmospheric heating, radiation, conduction, and convection, they can also end up by creating traveling ionospheric disturbances. Joule heating, especially during geomagnetic storms. We have also solar terminator. That is when the sun sets and the separation between sunset and sunrise. So when there is sun and when it is going on the other side of the Earth. So that is then in that situation also you get atmospheric gravity waves, which end up by causing the traveling ionospheric disturbances. Other method by which the TIDs are generated are aurora activities in the aurora due to particle precipitation. You can also get traveling ionospheric disturbances by checking the instabilities, such as Perkin instability. Of course, this is the growth rate of those instabilities, especially those ones they occur during the night. Now, these are applications of TIDs, or I call them effect of TIDs on HF communication or on other phenomena. But in this paper, which was published by Nathaniel, so they were investigating how the amateur radio were used in America, and they were counting the number of availability of those of the operators. So in this figure, the top figure, you can see that the number were grouped according to the range in kilometers, and they found that the number of people who were affected or who were where the signal were received, because sometimes you receive signals, sometimes you didn't receive signals. Then when the signal is received, they count it as number 1, number 2, number 3. When they don't receive it, it is not counted. So in this structure, you can see that the number which were received were decreasing, increasing, decreasing, increasing, decreasing, and so forth. So they tried to find why those signals, the number of people who were being, where the signals were received were decreasing and decreasing. They used this SuperDAN. SuperDAN is the instrument which is HF also. It is in HF band between 3 to 30 megahertz. So they used the SuperDAN. They found that the SuperDAN recorded a similar structure to the one which were recorded by amateur radio. They also use the GPS in total electro content. They found also that there is a similar structure where the TEC were prescribed. Of course, they concluded that there was TID. The TID were causing this radio in America to disappear and appear periodically, because people were okay, the signal where the signals were received were increasing, decreasing periodically, and they found that the period was around the 2.5 hours. So that means that TID can affect HF communication. You may have your instrument radio trying to call someone, but when there is a wave passing, your signals may not reach that person, or they may break depending on the period of that wave. Basically, how does it happen? The next slide explains how it happens. So when you send the signal to the ionosphere, it is reflected back to the receiver. Sometime when there is a wave, so this is the perturbation of which shows that there is a wave, the signal may focus or come together. So when they focus, that is when you receive the signal. But when they defocus, that means your signal may be sent away because the electrons is not the same, is not homogeneous. Then your signals may be sent to another place somewhere, and then they may not reach the receiver. That is how the TID affect the communication, especially HF. So now TIDs can also be used to warn about the arrival of a tsunami, especially in the region where you have many occurrence of those kind of waves, tsunami. And as we know, the tsunami can kill many people, especially when they hit a given city or a town. So in this paper, Shinshan, they found that the tsunami which were generated, I think, by a volcanic in ocean, they can also generate TIDs in the ionosphere at the same time. So you generate tsunami and they generate TIDs at the same time. But they also found that TIDs move very faster than the tsunami. Tsunami moves very slowly compared to the TIDs. So then once you receive the TIDs and you know their parameters, period, speed, whatever, you can mitigate or you can know that these TIDs are from the tsunami. So then you can expect how long should I expect the tsunami after after receiving the TID signals. So in the future, of course, people who will have the advanced instrument to detect and analyze the TIDs can use this as a warning to people who are staying in a region where tsunami can affect those people, especially I think in Japan. Now we did the study of TIDs and the near-range echo. Last year we published this paper in JGR. We were doing the statistics and we found that there is day-to-day variability of those TIDs. There is also seasonal variability of the TIDs as well as the solar activity. So they depend on solar activity as I have introduced by the space weather. This is sunspot number. So I was comparing TIDs and sunspot numbers. So we found that, as you can see, that most of TIDs, they have they lasted between 4 and 8 hours. And in most of them, they occurred during the night, which is from your 15 local time to around the 5 a.m. So most of them, they occur during that time. And we also find that this is summer, this is the equinox, and this is winter. So we find that most of them, they occur during summer and equinox. And during this period, during the summer, we conclude that because they also occur during the night, we conclude that most of them, they were caused by perking instability, because that is when those instabilities take place. So we can see that also there is the dependence on the solar activity, which of course doesn't have anything to do with the generation mechanism, but they were affecting the instrument. So geomagnetic storms can affect the instrument which were detecting the TIDs. That is how, when the sunspot reduced, the activity increases, which means they were detecting many activities during the period where there were less number of sunspot number. Now, another paper which we published last year is the TID's effect on sporadic E. Sporadic E also is known to be used, it can be useful for HF communication in two ways. It can be bad and good. It can be used to reflect the HF communication. Also, it can absorb the HF radio signals. So we published this paper in the Journal of Atmospheric and Solar Terrestrial Physics, where we demonstrated that TIDs that are propagating at around the 300 kilometer in ionosphere can affect sporadic E layer at around 100 kilometer. And of course, now we are going to introduce another part of the atmospheric gravity waves, but by looking on the advanced theory. So basically, for a student who want to study atmospheric gravity waves, they will be using, if they are analyzing data, they will be using those simple formula. But if now they want to follow the modeling or simulation or other advanced theory, now they can go to the next part we are going to talk about. Because this is the part, it's not my original slides, but they were presented by this specialist, Sharon Vadas, in 2008 when he was receiving a prize. So basically, atmospheric gravity waves are generated and they can propagate and they can dissipate. So to dissipate, we can maybe try to say that they can die or they can disappear. But as you know, energy is not destroyed nor created. So what happened? They have to be converted to another kind of wave or hit the region. So this figure shows that the same wave which is generated can take different amplitude or different parameters. It can change forms. That is how actually they end up by becoming very big, and they end up by disappearing or dissipating. So to study this kind of waves, you have to first look at the conservation of momentum, conservation of mass, and the conservation of heat through this formula by Navier-Stokes. Of course, if you did the fluid equations. So once you have those conservation equations, now you have to know to try to solve those equations. So what we can learn from this here is that once you move upward into the atmosphere, the density decreases very quickly, exponentially. Once the density decreases, it means that when the wave is propagating in a lesser or a less denser medium, its amplitude grows. And once it grows, the everything, even in the speed, the wavelength, everything grows exponentially. Then you need to solve to get the dispersion relation, which is divided into two parts here. You have a sound wave and you have a gravity wave for this part. So you focus on this part because we are dealing with gravity waves. So you ignore the sound wave. And after getting that dispersion relation, you have to try to obtain, to check where the dispersion is weak in the dispersion relation. And you have, of course, to get some assumption to make your calculation easier. Now, you need to solve and get the number the wave numbers. This is wave number in horizontal, and this is the which has actually 3 dimensions. And of course, you have to also get the wave amplitude. Once you get the wave amplitude, your atmospheric gravity waves will dissipate according to others, that will dissipate once the ratio of the speed and the angular frequency is almost equal to the density scalar height. So once these two are almost the same or almost equal, your atmospheric gravity waves are going to disappear or to dissipate. So they did this study here, and they found that their gravity waves were dissipating at around 150 kilometer in altitude, which is in the E region. So those are the figure to demonstrate that here you have a wave activity, but as the time, or if they move upward in the ionosphere, they dissipate and they end up by increasing the wavelength. So once the wavelength tends to infinity, which means it is stretched, that means the wave, once it tends to infinity, you no longer have a wave, it is dissipated or it disappear. So now, how do you study those gravity waves? You must do the ray tracing. So here ray tracing is you're trying to mimic the propagation of the wave using the signals, the ray signals of an instrument. So here the ray tracing involves to find the group velocity, you get wind parameters, and you get frequencies. So especially you have to find those derivation which are called analytic derivative of the gravity wave dispersion relation. So when you are doing the ray tracing, you must have this dispersion relation and try to derive those parameters to find the group velocity. So after solving, you get something like this. You get the group velocity in the zona, which is east, and meridiana, this is south north. You get also vertical component of the group velocity. Then once you get those parameter, the group velocity is the one that tells you where the energy of the wave is propagating to. Then you can now say that you have studied the gravity waves. So, in summary, we have found that the energy is neither created nor destroyed. It is conserved. You can only change its form, which is called transformation, or you can change, you can transfer the energy from one place to another. That is called the transfer of the energy, or most of the time, the transfer of energy is known as the heat. So you can heat or change that energy into heat. We have also found that solar wind, coronal mass ejection, and solar flare come from the sun and impacting our atmosphere by causing different phenomena in our ionosphere. An example of the phenomena that can take place in the atmosphere are called the waves. Those waves, we have found that you have a planetary tide atmosphere, atmospheric gravity waves, and many others. Atmospheric gravity waves, Perkin instabilities, Lorentz force, Joule heating, and other mechanisms can cause traveling ionospheric disturbances. And TIDs, or traveling ionospheric disturbances, are known to impact high-frequency communication. By the way, those high-frequency communication are used in military application. So at the end of this presentation, we have looked at the advanced theory of gravity waves. And if you are interested, of course, in doing modeling or simulation or studying into deep the gravity waves, you have to use those advanced theory of gravity waves. Okay, thank you. I think now I don't know if you have many students, they can do this quiz. We can take 5 minutes, or I don't know how long do we have? 5 minutes, then we can look the answer together at the end. Thank you very much.
Okay, thank you so much, Dr. Alicreance. You have given us an assignment which we may take about 5 minutes to resolve. So I think let's work out the assignment in 5 minutes.
Okay.
And then we will bounce back to
Together.
resolve that, yes, as
Okay.
well as have some short time of discussions around the topic you have presented.
Okay, maybe I can explain the question.
Okay.
I actually imagined this question. It is not taken from any book, or so. I just assume that in 2020, during COVID, we assumed that there were 4 peaks. Maybe let's assume that it was in South Africa. Then those 4 peaks, the first one occurred in March, at the end of March, the other one at the end of June, the other one at the end of September, the other one at the end of December. So which means it started in January up to December. Now we are assuming that this year had 360 days, which means all months are equal. Each one has 30 days. So the question is, I want to understand if students understand what is a period and what is a frequency. Because once you understand the period, you know that TIDs, if you study the waves, you will have an application even in medicine or other fields. So I want to know what was the period of the COVID waves in that country, because it had 4 peaks in the whole year in 2020. And I want to know, number B, how many peaks were found in each day? So every day, how many peaks did we have? That is your daily frequency. And the last one is how many peaks were found in every 3 months, or the number of peaks per 3 months. So I think they are very simple. I have given you the formula, so you have to remember that the period is time divided by circles, and the frequency is circles divided by time. So here circles, I think you can refer circles as peaks. If you can use peaks also, I think it's the same. Then we can do this in 5 minutes. Thank you.
Yeah, thank you so much. I think in this context, we are all students. Any participant here is seen as a student.
Okay.
So I think
I'm not going to mark it. You can check if you.
Yes. I think we can work on it, all of us.
Okay.
So I think if anyone has figured out the answer, the person can raise his hand so that we can recognize him to give us his answer.
Okay. So you have to choose one in A among those 3, and you choose one in B, you choose one in C. Oh, sorry. Okay, the last one is C. Sorry, my mistake.
Good morning.
Good morning.
Hello?
Okay, go on.
I'm seeing that the repetition is after 3 months.
Is that a sub-question A?
Yeah, I'm trying to analyze and answer question 1.
Yes.
Yes, the repetition is every 3 months.
Okay, that is your period.
Yes, so every 3 months we are down many months. June, September, December.
Yes.
So there are 3. Is it 3? 1, 2, 3.
You have the 4 peaks.
From what I can see, so 3 times 30. That should be 90 days. Now the period is number of cycles, the time over number of cycles. Yes, so 90 period over number of cycles. So it was repeating every 3 months. So 3, 1, 2, 3. There now many months? 3.
I think you have an answer. Once you are saying it was repeating that repetition,
Yes.
That is your
every
period.
3 months. So 1 cycle, 3 months, meaning we have 3 cycles.
Yes, that is your period. Your period is every 3 months. Because it is coming back every 3 months. That is your period.
One cycle every 3 months.
Yes, that is your crest or your peak or whatever. So that is your period is going to be 3 months. The answer is C, but I hope everyone got it right. So the answer is C for A. Because you have a 360 days. You have a 360 days and you have 4 peaks.
If I'm taking the time that has been given, it means it's 90 days.
Yes, correct. 3 months.
Okay.
Number B.
How many peaks? They are supposed to be 4. One in March, one in June, one in September, one in December.
Every day.
No, how many peaks?
So that is the frequency. Frequency means many peaks, how many cycles per unit time. So now I want to know how many peaks every day.
Yeah. Here, I think.
How many peaks every day? I think I need to calculate that one. Let me wait for others.
Okay, yes. Then next one.
Yeah, the how many peaks per day, I think that should be the number of peaks divided by the number of days in a year, which according to my arithmetic here is option B.
D.
B as in boy.
No.
D or E? Sorry,
Option E.
It is E.
E, yes.
Correct. So your actually your frequency, it has to be the inverse of your period. 1 divided by your period, you get the frequency.
Yes.
Okay. And the last one.
How many peaks were found every 3 months? It was 1 peak.
1 peak.
Yes, every 3 months you get 1 peak. But you see now the people were struggling, and during COVID, you have waves coming. So if you understand the waves, because of course the waves, they are not always uniform. Sometimes they are complicated. If you understand the theory, you can use them to understand even the pandemic. Okay, thank you.
Okay. Thanks for that.
Okay. So the answers are C, E, and G.
Yes, C, E, G. Good.
Yeah.
Okay.
So now it's time for questions or discussion.
So it's now time for interactions around the topic. I can see one question on the chat.
Okay.
I think it was dropped by a man who says, do planets in the solar system, are planets in the solar system and dwarfs in the solar system affected by the solar wind from the sun? Did you get the question?
I understand the question.
Whether the planets and other objects in the solar system are affected by the solar wind from the sun?
The answer is yes, because you know Earth is a part of the planet. So we have, I think there are nine, or I don't remember if it are 9 or... So those planets, all of them, including the Earth, they are in the solar system, and the sun, it is send those solar wind around in all direction, I would say, in all direction. So when the solar wind blows into those planets, including the Earth, most of them, they are protected by their magnetic field. If they don't have the magnetic field, then of course, they are affected, badly affected, because they are not protected. But the good thing is that they don't have people who are living there, as maybe if people, they go to the moon or whatever, I don't know. But if they are there, then they can be affected if the Earth, that planet's magnetic field is not strong. But they are all affected as we are affected. Thank you for the question. Is that
Okay.
a
Sorry, I think that was a noise from the background.
Okay.
Yeah, so let me quickly drop this question. We have heard about what is referred to as a Fobos decreases. Now, these TIDs, are they related to the Fobos decreases?
Phobos.
Phobos.
What are they?
Phobos events are like a kind of variations in cosmic ray counts on the Earth.
Cosmic rays.
Yes, I think it's related to cosmic ray count. So is it connected with this TID?
Okay, so I'm not very sure about those events, but if they are cosmic event, I think they are not generated in the ionosphere. So which means they are generated far away from the ionosphere.
Okay.
So the TIDs, what they can do, if those cosmic waves are passing through the ionosphere, it can change the ionosphere, the way it is, the structure of ionosphere. And of course, if they pass through I don't know their wavelength or their characteristics, but if they are, because not all signals that are passed in ionosphere are affected, not all of them, but some they are affected. I know like X-rays, they are not affected, or EUV, whatever, those kind of signals are not affected. But if they can be affected, if they are in the range of HF, for example, between 3 and 30 megahertz, then definitely they can be affected by traveling ionospheric disturbances. It can also affect those HF communication. But I'm not sure if those cosmic rays can be affected by the TID.
Okay, thank you.
Sorry, Doc. I think you talked about solar winds, right?
Yes.
Yeah, then there is a possibility because solar winds, they are coming from the sun.
But solar wind is not affected by TIDs.
They are not affected by TIDs. They
Yes,
may affect the tip.
Actually,
Okay.
solar wind maybe can have an impact on the TID.
Okay.
Not the other way around.
Okay.
Yeah, because one of the mechanisms which can generate TIDs is called Joule heating. And when there is this solar wind is the amount of particles coming from the sun. They gyrate around the magnetic field to the pole. And that is phenomena sometimes is known as the particle precipitation when they reach the lowest level of atmosphere in the E region. So when the particle precipitation meet with other conditions, they generate Joule heating. So through that Joule heating, that's where you can generate actually the powerful or the large-scale traveling ionospheric disturbances that propagate from the pole to the equator. I think that's all.
Okay, thanks for that response.
Okay.
Yeah, more questions, more comments from colleagues. Okay, it seems there are no more questions and comments from our colleagues.
Okay. I think
Okay.
let me see in the comment. Do
Sorry,
gravity?
I can see a hand up, Aman.
Okay, I was
Yeah,
going to read the comments.
No, I can read the comments, and I just have one question. You can read the comments. I'll ask after the comments.
Okay, so all right. I see this one of do gravity waves from black hole affect Earth's weather? I know they discovered the gravity waves from black holes, but I think they are far away from our solar system. If they can reach the solar system, of course, the energy is neither destroyed nor created. They can affect it in one way or the other, but those are, the effect, I think they are going to be minor. So the way it depends on the energy they will reach in the solar system with, but I don't know if they can travel from where they are up to our planet, our Earth. That is what I think. I don't have much information on the gravity waves generated by black hole if they reach this environment of ours. Another comment, I think, where magnetosphere and plasmasphere located in the Earth is a magnetosphere. What is the definition of TIDs? Okay. Magnetosphere, as you can see, there is a word magnetic field. So the Earth has a magnetic field which protects us from the effect of space weather. So that magnetosphere, I can't tell you exactly kilometers, but it is far away, thousands of kilometers away from the surface of the Earth. And I think it is plasmasphere. Plasmasphere is around, I think it is above the ionosphere in the exosphere. So the magnetosphere is that sphere around the Earth which protect the Earth from the harm which are coming from the sun. Now, the definition of TIDs, TIDs are the waves, perturbation in the electron density or ions of the ionosphere. So any wave that are propagating in the ionosphere, sometimes they call them plasma. If they propagate in that plasma, they are called traveling ionospheric disturbances because, of course, they are moving. They move from one place to another one. So that is the definition of TIDs. And how do solar wind, solar flare travel in binary stars system, and how do they affect the exoplanet? I think this question is more related to astronomy. Solar wind and solar flare travel in binary stars. So I know the sun is a star, but I don't know exactly how do they travel, those solar wind and the solar flare travel to the binary stars. What I know is that solar wind from the sun and solar flare, actually, they travel at different speed because solar flare is much faster and solar wind, they are slower. So the solar flare, they travel at the speed of light, while solar wind, they move at a speed between 400 and 1,000 kilometers per second. So I don't know if it is the same in the binary stars. And how do they affect the exoplanet? So I don't have any information about this exoplanet. I think this question is more related to astronomy.
Astronomy, yeah.
Yeah. Okay, so there was someone who has a question.
Aman has his hands up. Aman.
Yeah, good afternoon, professors. My question is that can these waves or TDIs be used as renewable energy? And to also add that the Wi-Fi cut my signal. So what was the correct answer to question 1 and question 3? Because I know the correct answer to question 2 is E. And back to the thing, can TDIs and waves be used for renewable energy? Can TDIs and atmospheric waves be used for renewable energy? Yes.
I understand your question.
Okay.
Okay. So that is a very important question, which actually is challenging, because from the definition of energy, energy is not created, and it can't be lost. So those waves, gravity waves and TIDs, they can be used, but I think it is going to be very expensive. If you never know in the future, because in the water, we know the ocean waves are being used to generate electricity. And even wind can be used to generate electricity. But who knows, TIDs, if you can be able to install some equipment in the ionosphere, or some instrument in the ionosphere that can generate electricity and transfer that electricity to the Earth, then that will be very interesting, because it is a renewable energy that is not being exploited at the moment. But in the future, you never know, with the technology and the improvement of science, it may be possible. So your another question, what was the second question?
The second question was asking what was the answer to all 3 questions.
Oh, okay. Let me go back.
My Wi-Fi cut. Because my Wi-Fi cut.
Okay, what did you answer?
Well, my first one I put C, the second one I put E, and the last one I put I or L, whatever.
Okay. So the first one was C, you got it right. The second one is E, you got it right. But the last one is not correct, because it is written here. So the peak were recorded on the last day of March, June, and they all have the same days. So each month has 30 days, which means from January to March, how many months do you have?
January to March, isn't it 3 months?
And from March to June?
3 months.
From June to September?
3 months.
From September to December?
3 months.
Then you have only one peak every 3 months, which is the period.
Wait, but why is it only one peak, not 3?
3 peaks?
Yes.
It's because we had, maybe you have to understand the question. So we had 4 peaks throughout the year. So which means one peak in March, one peak in June, one peak in September, another peak in December. If we could have a 3 peaks, or a peak, I don't know how you are calling it, if it is a peak per month, we're going to have a peak in January, a peak in February, a peak in March, a peak in April, May, whatever, each month. But we did not have anything in February. There is no peak in February.
Oh, okay.
There's no peak in May. Do you understand?
Yes.
So we don't have a peaks. We only had the peaks in March, in June, which is means after every 3 months. That is your period. Now, the frequency can be given in any unit of time. Actually, the SI unity of the frequency is hertz, which is 1/2. So they can even ask you how many peaks do you have every second? Then you have to divide those days into whatever.
So it's just asking for
Exactly.
the 3 months, not for the whole year. That's what it was asking for.
Yes, it was asked how many peaks were found in every 3 months.
Oh,
January, February, and March. How many peaks did you find there? It is only one.
One.
Yes.
And from April, May, and June, how many peaks?
April,
One.
May, and June. Oh, yes, one.
The easy way to get that number is now to take the number of the total time, which was a number of 360 days. You divide by 12, which means you get one. Was it? No, you divide by 4 to get 3 months. So once you divide by 4, you get 3 months. How many peaks did you have in 3 months? So it is you had 4 peaks per 360, which means every 3 months you had 1 peak. Okay, well, actually, I want to rephrase this question. So this answer is that you have 4 peaks in 12 months.
Yes.
That is correct. So in 12 months, you have 4 peaks. So every 3 months, you have to divide that 4 peaks per 4. So when you divide the 4 by 4, you get 1, which means every 3 months, you get one peak. But that is it's simple. You can even write down and try to see if it is
So
correct.
you rounded the 0.11 to the whole number 1 peak because E was correct.
No, that is not
0.11 was divided to 1.
That is a frequency.
Oh, okay.
That is a frequency per day, every day.
Oh, okay.
That is B. In B, if you actually it is not even 0.2. So there are many ones after the dust number. So what you were supposed to do here is to understand the question. Once you understand the question, don't just go to formula. First understand. Because the question number B and the C, they are all the same. They're asking you about the frequency. The frequency. So you have to understand what is a frequency. A frequency is how many times something is happening per unit time.
Yeah.
So how many times do you sleep per month? So now I can ask you how many times do you sleep per year, which means you have to multiply. So it is the same thing.
Yeah, it's okay. Thank you, Dr. Alicreance.
Wait, just one last thing to add. If I want to do your field on gravitational waves or do the topic of what that you presented, what subjects would I need to take or topics would I need to take in university? Or what area or job would I need to major in to do what you were presenting?
Which level are you now, undergraduate?
Yeah, I'm going to do my bachelor's soon.
Bachelor. Okay. So there is a course which is called the oscillations and waves. If you can do this course, but of course, if you are doing, you must do physics. I think all physicists they do this course. Oscillation and waves, where you will study the string, the whatever, the water, the interferences, So those are the subject you have to do. And you were asking also the application or what? There was another...
The career, the job I need to take to do what you were presenting on.
Okay, career.
Yes,
But
career opportunities.
so yeah, as you see, there are many opportunities once you follow physics. Of course, you can't just go and say, I'm going to study only waves, especially at your level. So you have to study physics, they have to teach you some mathematics, they have to teach you some statistics and other stuff. Now, once you come, if you want to continue in doing research, for example, you have now to go to honors and do the masters and do PhD. That's how you start to narrow and go and focus on the waves. So now once you understand those waves, you can become a researcher, you can become a lecturer, you can do many things. So it doesn't mean that once you are trained in the waves, or let me call it theories, it doesn't mean that you understand only this. As you can see, I have composed this question. So this question, I did not read it from any book, but from my understanding of what is a wave, I just imagined, how can we create a question of a wave using the COVID pandemic and then use it? So once you have a PhD, it's a degree of philosophy. People, they trust you that you can handle any situation. So you are able to do many different types of jobs. So you are a candidate to many positions, either private or government, and so on. So I think the first ones is to do research and do the lecturing, but also you can do this signal, like those who are working in communication. If you are working on, those MTN, the transmitters, the antennas, those kind of things, they are all using waves. I think that's what I can say on that question.
Yeah,
Thank you
thank you so much.
professors for answering my question, and thank you for the insight. I appreciate it. Thank you very much for giving me insight into your jobs, and appreciate it. Thank you both for allowing me to answer the question. And please continue to update me on the seminars. Thank you, professors.
You're welcome.
Enjoy.
Thank you, Harun Alman. I think you are an active participant in what we are doing, and we thank you for that. We really appreciate you. I think at this point,
You're welcome.
we want to summarize. There are no hands up, and I think we have exhaustively discussed the topic. Colleagues have asked their questions, which have been beautifully addressed by the presenter. So, Dr. Alicreance, I thank you for making out time to be part of this seminar, and for the beautiful presentation you have given to us. I do hope that whenever we call on you again, you will be there to respond to our needs. So I'm happy that you were able to make it despite the forth and back procedures we used in getting you into the program. I am sure that you will come again, because more programs are still on the way, and I will get in touch with you as the whole thing unfolds.
Thank you very much.
Once again, I thank everybody who made out time to be part of today's seminar. And as we have pointed out, we have this seminar regularly every month. Just around the second week of every month, we'll have a seminar, except if something very important intercepts that. Otherwise, it's a regular program on FAST4Future. So, ladies and gentlemen, at this point, I say we call it a day. And thank you again.
Thank you. You are welcome to let me know when you want me to present something on the space related topics. Thank you so much.
Yeah. Bye.
Okay, bye.
Bye.